Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will talk about another popular probability distribution. We will talk about the geometric distribution. As usual, our discussion will be based on an example. Here's our plan. So, using this example, we are going to discuss in detail the characteristics of the random experiment that yield to a random variable to have a geometric probability distribution. We're going to talk about its sample space. We're going to derive the probability mass function for that particular example, and then we're going to use R to find probabilities that could be of interest when dealing with that kind of random variable, a geometric probability distribution. Okay, let's begin. Let me borrow that example from our lecture notes. Okay, that's the example I would like to discuss with you today. So, according to a recent study, right, we have that Pepsi has a market share of 26%. Okay, meaning 26% of soft drinker users are, will prefer Pepsi. Okay, so a marketing research firm wants to conduct a new taste test, and for that test they need Pepsi drinkers. So what they need to do is to find Pepsi drinkers, right? So what they will do is just screen the population of soft drinker users and identify among them Pepsi drinkers. Our problem is finding the following probabilities. That the first randomly selected drinker is a Pepsi drinker, right? That they need to contact two soft drink users in order to find their first Pepsi drinker. Then we would like to find a similar probability, meaning what is the probability that they need to interview 3 individuals in order to find the first Pepsi drinker. Then we're going to do the same. We're going to find the same probability, a similar probability for 4, and finally we're going to extend that to K, where K is any natural number, meaning 1, 2, 3. Make sense? Okay, so that's the ultimate goal. As we said, first we would like to describe in detail the characteristics of this random experiment. So that's what we're going to be doing next. Characteristics of the experiment. So note that what we're going to be dealing with is a sequence of identical trials, and the goal for each trial is the same: identifying a Pepsi drinker. As you can see, each of these trials has 2 possible outcomes. One is going to be labeled as a success. Our success in this particular case will be if the soft drinker user is a Pepsi drinker. The other possibility, the other possible outcome is a failure, and that would be the complement, that the soft drinker interviewed is not a Pepsi drinker. Okay, and we're going to be labeling that failure with an F. Okay, that's the notation that we're going to be using. Based on the information that we have about the market share of Pepsi, and we have that it is 26%, we are going to assume that that 26% is the probability of success, and that probability of success remains constant from trial to trial. Okay, and finally we have an assumption that the outcomes of this random experiment are independent. So soft drinker users are assumed to be independent. Okay. So now that we have discussed the characteristics of our random experiment, let's try and answer these questions. Okay, let's start with the first one. What is the probability that the first randomly selected drinker is a Pepsi drinker? Okay, here we go. So, solution. So we have discussed in detail the characteristics of the random experiment. Let's define our random variable of interest. So in this case, the random variable of interest is the number of trials performed until the first success occurs. Okay? And in this case, we know that a success is identifying a Pepsi drinker. So the first part is finding the probability that the first person interviewed is a Pepsi drinker. So probability of y being equal to 1 is the same as the probability of the following event, the probability of a success. And according to the information that we have, right, the probability of observing a success is 26% or 0.26. Okay, so that one was easy. Now let's find the probability that we need to interview two soft drinker users in order to find our first Pepsi drinker. That is equivalent to the probability of the following event: a failure and a success. You agree? Now, remember that we had this assumption that soft drinker users were independent. That's our assumption. That assumption is going to be very useful here, because by assumption of independence, then the probability of that intersection is going to be the probability of F times the probability of S. But let me just write that down. By independence, that probability will be just the following product. The probability of F intersection S equals probability of S times probability of S, probability of failure, sorry, probability of failure times probability of success. And let me write it down like this. We know that the probability of success is 0.26, therefore the probability of failure is 1 minus 0.26. Make sense? Okay, let's find it. Let me use R to find that probability. Let me launch R, and then we have 1 minus 0.26 times 0.26. Okay, so it's 0.1924. Great. Let's find now the probability that we need to contact 3 soft drinker users before finding our first Pepsi drinker. So probability that y equals 3 in that case is the same, is equivalent to the probability of an F and then another F, so failure, failure, and finally success. As you can imagine from what we did before, we are going to be using our assumption of independence again. That is going to allow us to find the probability of that intersection easily. So by independence, what we have is a product of probabilities going to be the probability of F times the probability of F times the probability of success, which would be the same, would be equivalent to probability of failure squared times probability of success. Now we know that the probability of a failure is 1 minus 0.26. We're going to be squaring that, and the probability of success 0.26. Let's find that number. Let's use R to find it. So would be 1 minus 0.26 square times 0.26. In this case, that's roughly 14%. Let's do 4, and then we are going to provide a formula, an expression in the case of k, where k is going to represent a number that is greater or equal to 1. Okay, so let's do the same for 4, and then we are going to find the general expression. So when y equals 4, what we need is first 3 failures, right? Because what we're saying here, remember that y is the number of trials until our first success. Okay, so in this case we need 3 failures first, and then the 4th trial is a success. Again, using independence, that is going to turn into a product of probabilities. The probability of failure remains constant because the probability of a success remains constant from trial to trial, and then this is just the probability of failure cube times the probability of success. We know that the probability of failure would be 1 minus 0.26 cube right, and then times the probability of success. Let's find that number using R. So now instead of 2 we have a 3 here, and the probability that y equals 3 will be roughly 0.10 or 10%, meaning that would be the probability that we need to contact 4 people before being able to detect our first Pepsi drinker. Make sense? Okay, so we're almost there. Now we're going to be doing this for any k, where k could be 1, 2, 3, any number greater or equal to 1. So let k be a number greater or equal to 1. So what we're going to be doing is finding the probability that y equals k. Okay? That we need to contact k people, k soft drinker users, before identifying our first Pepsi drinker. So note, let's see what the pattern is, and then it's going to be easy to write it down. So if y equals 1, then the first one was a success. Okay? Now note, if y equals 2, that means that we had first one failure, and the last one, the last trial, was a success. So we have 2 and 1 here. If y equals 3, that means that we needed to experience first 2 failures, and the third trial was a success. So 3 and 2. Finally, if we needed 4 trials to get our first success, that means that the first 3 trials were failures, and the last one was our first success. So the difference between these two is 1. So if we needed k trials to get our first success, if we needed to contact k soft drinker users in order to find our first Pepsi drinker, that means that the first k minus 1 were failures. And the last one was a success, which means that this probability will be given by 1 minus 0.26 to the k minus 1 power times 0.26. Make sense? Okay, so that formula that you got here would be the probability mass function of a geometric random variable. Okay? Or another way of saying it is that this is the probability distribution for a random variable y with parameter p equal to 0.26. Okay, and note that the possible values for y, right, y could be 1 or 2 or 3 or any positive number, right? Note that in theory it could take us any integer to find our first success, and we could find that probability for any positive integer. Make sense? Okay, so let me show you a graph of that probability distribution. Let me go back to our lecture notes. I think that I have it here. Okay, yeah, that's what graphical representation for a geometric distribution looks like when the parameter, the probability of success is 0.26. Okay, looks like this. Okay. Now, how about we try and find those probabilities more quickly? Okay. It turns out that there's a built-in function in R that is going to help you find probabilities for a random variable whose distribution is geometric. Okay? Now, something that I want you to pay attention to is the way that random variable is defined in R. Remember that in our case, y, let me go back here to the definition of a random variable, y represents the number of trials performed until our first success. Okay? Now, if you're going to be doing things with R, and that's why I used a different letter, X. If you want to do calculations for a geometric distribution using R, the random variable X represents number of failures until your first success. So for instance, in our case, if you needed one trial, okay, to get your first success, that means that you had 0 failures to get your first success. If you needed one failure to get your first success, that means that you needed 2 trials. Make sense? So just be careful. Okay? So let's see these 2 lines of code should give you this output. Let me just copy and paste those to double check. Yeah, it works. So anyway, just keep that in mind. If you're going to be doing calculations using R, okay, just keep that in mind, that In the case of R, the random variable is the number of failures until the first success. In our textbook, the random variable is the number of trials until your first success. Okay? Now, finally, let me show you the formula that we are going to be using in our textbook, right? That comes from our textbook. So a random variable is said to have a geometric probability distribution if the formula looks like this. And this is what we had in that particular case. Note that P is the probability of success in any given trial, and for that particular example, P was equal to 0.26. And these are the possible values for that random variable, because Y again represents number of trials performed until the first success. So you need to try at least once to get a success, right? So, and as we pointed out earlier, the possible values for that random variable Y are infinitely many. It could be any positive integer. Make sense? Okay. So just to summarize, with that example, what we did was giving an example, an illustration of the kind of random experiment that results in a random variable having a geometric probability distribution. And we derived the probability distribution for our particular example. And we realized that it has this kind of expression. 1 minus the probability of success to the power Y minus 1 times probability of success, where Y is the number of trials until your first success. And we also learned how we can easily, quickly find these probabilities using R. The only thing is that we have to pay attention, and if we're going to be using R, we have to keep in mind that in the case of R, they count a different random variable, the number of failures until the first success is observed. Okay? Well, that's it for now. Thank you so much for watching. Please keep working hard and take care. See you next time. Bye.